Welcome! In this linear algebra tutorial, we're going to do some problems on linearly independent vectors, linearly dependent vectors, basis, and dimension. So if you're interested in that, then stick with me. Okay, question 1. Determine whether or not u and v are linearly dependent, where u and v are given by the vectors, say, in part A. All right, so what does this mean, linearly dependent? Well, it means that if you have alpha u plus beta v, they're dependent whenever this is 0, it implies that alpha and beta are not all 0, okay? But if you only have two vectors u and v, then linearly dependent means that one of the vectors is a scalar multiple of the other vector. So that's what we should do here, because we only have two vectors. So in part A, we have u is the vector 1, 2, v is the vector 3 minus 5, and we're asking the question, do we have u equal to t times v for some real number t? Okay, because if we do, then those two vectors u and v are linearly dependent. So let's try this here. All right, so we have then, if this is true, we have 1, 2 equals t times 3 minus 5. Okay, and so if we expand the right-hand side, we get 3t minus 5t, and so then that gives us two scalar equations from this one vector equation. It gives us 3t equals 1 and minus 5t equals 2 as a simultaneous system. All right, so now taking the first equation, the first one gives t is equal to 1/3, but that doesn't work for the second one, because if we put this into the second equation, we have minus 5 times 1/3 is equal to 2. And so 2 is not equal to minus 5 over 3. This is a contradiction. Okay, so by this I mean a contradiction. So we'll say then that u and v are not linearly dependent, they're linearly independent, like so. All right, moving on to part B, we have u equal to 1, 2 minus 3, v equal to 4, 5 minus 6. Okay, and so again, suppose that u is equal to t times v for some real number t. Well, if this is the case, then we have this. Now expanding the right-hand side gives 4t, 5t, 6t, and so equating that to this vector gives us three scalar equations from the single vector equation. So we have 4t equals 1, 5t is 2, and minus 6t is minus 3. And so from the first one, t is a quarter, but 5 over 4 is not equal to 2, because this here says that they're equal, but they're in fact not equal. And so we have a contradiction to the assumption that these two vectors are linearly dependent. So again, u and v are linearly independent. All right, part C, u is 1 minus 3, and v is the vector minus 2, 6. Okay, so suppose again that u is equal to t times v for some real number t. Now the question is this the case? Okay, so following this assumption, we have this. Spanning the right-hand side gives minus 2t, 6t. And so this gives rise to two scalar equations. Minus 2t is 1 and 6t is minus 3. Now the first one tells us that t is minus a half. Is that consistent with the second equation? And yes, it is, because 6 times minus 1/2 is equal to minus 3. 6 divided by minus 2 is minus 3. And so this is consistent, and there is no contradiction in this assumption. In fact, what we've learned is that we have u is equal to minus 1/2 of v, and so these two vectors are linearly dependent, but I'll show you some more details on that. If we multiply both sides by 2, say, and add v to both sides, we get 2u plus v is the 0 vector, and coefficients 2 and 1 are not both 0. So u and v are linearly dependent. So they depend on each other. And in fact, they're parallel vectors. So if we sketch these vectors, u might look like this and v might look like this. So I'll just write parallel. But again, keep in mind that if you have three vectors, when three vectors are parallel, they are linearly independent. However, that is not the criterion for those vectors to be linearly dependent. Just bear that in mind. Okay, part D. Okay, so we have these two vectors u and v. Are they linearly dependent or linearly independent? So again, since we only have two vectors, suppose u is equal to t times v. So if that's the case, then 2, 4 minus 8 is equal to t times 3, 6 minus 12. Expanding that right-hand side gives us 3t, 6t minus 12t. Okay, now this is one vector equation that gives rise to three scalar equations. We have 3t equals 2, we have 6t equals 4, and we have minus 12t equals minus 8. Now the first equation gives us t equal to 2/3. If we take this and substitute it into the second equation, 6 times 2/3 is 12/3, which is 4. That's true. We sub this into the third equation. Minus 12 times 2/3 is minus 24/3, which is minus 8. This is consistent. And so given that it is consistent, we have u is equal to 2/3 v, which we can write as u minus 2/3 v is the zero vector. And so since these coefficients 1 and minus 2/3 are not both zero, these two vectors are linearly dependent, which I've written there. Question 2, determine whether or not u and v are linearly dependent for these vectors. So in part A, we have u of t is a polynomial, 2t squared plus 4t minus 3. Similarly, v of t is a polynomial. Okay, so let's assume that there exists some scalar alpha such that alpha times u of t is equal to v of t. Okay, well, if that is the case, then multiplying alpha times u, we have 2 alpha t squared plus 4 alpha t minus 3 alpha equal to 4t squared plus 8t minus 6. Okay, now matching coefficients, we get 2 alpha equal to 4, 4 alpha is equal to 8, and minus 3 alpha is equal to minus 6. So the first equation tells us that alpha is equal to 4/2, which is 2. That is consistent with the second equation and consistent with the third equation. And so then what we can conclude is that 2u of t is equal to v of t, which means that the vectors, or these polynomials viewed as vectors, are linearly dependent. And so we could also write this in another way. We could write 2u of t minus v of t equals 0. And we see that since these coefficients 2 and minus 1 are not all 0, again, we see the vectors are linearly dependent because they're not forced to be all 0. Okay, 2b. Again, we have two polynomials. And so again, let's suppose that alpha u of t is equal to v of t. Then if that's the case, then 2 alpha t squared minus 3 alpha t plus 4 alpha is equal to 4t squared minus 3t plus 2. And so matching coefficients, we get 2 alpha is 4 minus 3 alpha is minus 3, 4 alpha is 2. Now the first equation gives us that alpha is 4/2, which is 2, but that is not consistent with the second equation. In other words, minus 6 is not equal to minus 3. And so we have a contradiction to the assumption that there exists an alpha that makes this true. And so what this means then is that u and v are linearly independent. Okay, 2-part C. This time we have two matrices. We're going to view these as vectors. Okay, now again, because we only have two of these that we're looking at, assume that alpha times u is equal to v for some real number alpha. If this is the case, then alpha, 3 alpha, minus 4 alpha, 5 alpha, 0 minus alpha is equal to the vector v minus 4 minus 12, 16 minus 20, 0, 4. Here's one vector equation that gives rise to 6 scalar equations. Okay, and so these scalar equations, we need to have a look whether they're consistent. So the first one says alpha is minus 4. The second one, if we take that minus 4 and sub it in, we have minus 12 equals minus 12. Okay, if we take minus 4, sub it into the third equation, we have 16 equals 16. That's consistent. In the fourth equation, 5 times minus 4 is 20 minus 20. So minus 20 equals minus 20. Yes, consistent. 0 is equal to 0. Yes. And minus 4 is plus 4. That's consistent. And so what we have then is that v is equal to minus 4 times u, which we can write as 4u plus 1 times v is the 0 vector. In this case, the matrix consisting of all 0 entries. But since we see that those coefficients are not forced to be all 0, we see that the vectors u and v here are linearly dependent, as I've written there. Okay, 2 part D. Again, we have 2 by 3 matrices, which are our vectors in this case. And so suppose alpha u is equal to v, where alpha is a real number, then alpha, 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 2 alpha, 2 alpha, 2 alpha is equal to v, which is 2, 2, 2, 3, 3, 3. So we see here from matching entries that alpha would have to be equal to 2 from the top row, but that is not consistent with the second row, which says that 4 is equal to 3. This gives a contradiction to the assumption that there is a real number alpha such that alpha times u is equal to v. And so we see then that u and v must be linearly independent. Question 3, determine whether the vectors u equal to 1, 1, 2, v equal to 2, 3, 1, and w equal to 4, 5, 5 are linearly independent. Now these are in 3 space and we have 3 of them. So the way we need to set this up is to suppose that there exist scalars alpha, beta, and gamma such that alpha times u plus beta times v plus gamma times w is the 0 vector, and see what happens. Can we find alpha, beta, and gamma not all 0 such that this equation holds? And if we can, then these 3 vectors are linearly dependent. If we cannot, if they are forced to be all 0, then they're linearly independent. Okay, so let's put these scalars in, multiply, expand, add up, and revisit this equation. So alpha times u is alpha, alpha, 2 alpha. Beta times v is 2 beta, 3 beta, beta. Gamma times w is 4 gamma, 5 gamma, 5 gamma. And we're supposing that this is 0, 0, 0, the 0 vector. Okay, adding these components together, we have alpha plus 2 beta plus 4 gamma. We have alpha plus 3 beta plus 5 gamma. We have 2 alpha plus beta plus 5 gamma. This is supposed to be equal to the 0 vector. Okay, so this single vector equation gives rise to 3 scalar equations. We have alpha plus 2 beta plus 4 gamma equal to 0. We have alpha plus 3 beta plus 5 gamma equal to 0. We have 2 alpha plus beta plus 5 gamma equal to 0. Okay, this is a system of simultaneous equations in alpha, beta, gamma. Now from this we can write a matrix equation, which just reading off the coefficients here, we have 1, 2, 4, 1, 3, 5, 2, 1, 5 times alpha, beta, gamma equal to 0, 0, 0. Okay, now look carefully here. What we have, this is u transposed to be vertical. This column is v transposed to be vertical. And the third column, 4, 5, 5, is w transposed so that we have a column. So let's just say note, this is u transpose concatenated with v transpose concatenated with w transpose times alpha, beta, gamma equal to 0, 0, 0. Okay, and now so we can write the augmented matrix for this and solve this using Gaussian elimination. So the augmented matrix is 1, 2, 4, 0, 1, 3, 5, 0, 2, 1, 5, 0. So let's now row reduce this. Okay, replacing row 2 with row 2 minus row 1. In row 2 we have 0, 1, 1, 0. I'll leave row 1 the same for now. Okay, now replacing row 3 with row 3 minus 2 row 1. We have 0, 1 minus 4 is minus 3. 5 minus 2 times 4, so minus 8 is minus 3, 0 minus 0 is 0. Okay, and now multiplying row 3 by minus 1/3, we'll see that it's the same as row 2. And so we can now replace row 3 with row 2 minus row 3 so that we have a row of zeros there. Okay, next, let's multiply row 2 by 2 so that we can put a 0 where this 2 is up here. So next, replacing row 1 with row 1 minus row 2, we have 1, 0, 2, 0. And replacing row 2 with 1/2 of row 2, so we return it to this. Okay, so we have exactly 2 pivots. I'm going to circle the pivots. So below this first pivot, we have zeros. Above and below the second pivot, we have zeros. These are only 2 pivots. We cannot have a pivot in the third row because it's all zeros. And so this is in row reduced echelon form. Okay, so now let's go back to the matrix equation. So it says this, and so now multiplying this out, we have 1 times alpha plus 2 times gamma. So alpha plus 2 gamma is 0. And then the second one says beta plus gamma is 0. So this shows us that we can write both alpha and beta in terms of gamma. And so alpha is equal to minus 2 gamma, beta is equal to minus gamma, and hence alpha beta gamma is minus 2 minus 1 1 times gamma, because gamma equals gamma. So that's how we get our third entry in this. So each of alpha, beta, and gamma can be represented in terms of gamma. So now let's go back to our original assumption here. The original assumption is, suppose there exists alpha, beta, gamma scalars such that this equation is satisfied. We actually found the alpha, beta, and gamma in terms of gamma. So think about what this says now. This tells us then that since alpha is minus 2 gamma, we have minus 2 gamma times u. Beta is minus gamma, so minus gamma times v, and then plus gamma times w. This is the 0 vector. Okay, now assuming that gamma is non-zero, we can divide throughout by that. And so we get then that minus 2u minus v plus w is the 0 vector. So we can check this like so. And so this first entry here is minus 2, minus 2, minus another 2, plus 4 is 0. So that's true. Minus 2 times 1 is minus 2. Minus 2 minus 3 is minus 5. Minus 5 plus 5 is 0. Minus 4 minus 1 is minus 5. Minus 5 plus 5 is 0. So yes, we in fact have this. We have found coefficients not all 0. So since alpha, beta, gamma are not all 0, we see that u, v, and w are linearly dependent. So they depend on each other. In other words, we can see that w is equal to 2u plus v. So w depends on u and v. So I'll just put note w equals 2u plus v. So depends on u and v. And I say that just to help you understand what linearly dependent means, that the vectors depend on each other. Question 4. Determine whether or not each of the following list of vectors in 3 space is linearly dependent. Okay, so again, alpha u1 plus beta u2 plus gamma u3 plus delta u4 equals a 0 vector. But what we can do is concatenate these, transpose it first, put these in columns of a matrix. So what we have then is u1 transpose concatenated with u2 transpose concatenated with u3 transpose, and then u4 transpose, and then the 0 vector. Okay, and so this is the augmented matrix. So this is 1, 2, 5, 1, 3, 1, 2, 5, 7, 3, 1, 4, 0, 0, 0. And what we want to do with this is row reduce this, seeking the row reduced echelon form of this matrix, so that we can understand the relationship between coefficients of the equation alpha u1 plus beta u2 plus gamma u3 plus delta u4 equals 0. Okay, so I'll write this down here like so. Okay, so now let's find the row reduced echelon form of this matrix here. corresponding to this. So let's multiply the top row by 10. Let's multiply the second row by 5 and the third row by 2. And the reason I've done that is so that I can have all 10s down here, and treating this top one as my pivot, I want zeros below that pivot, and now it's easy to see how to do that. So now replacing row 2 with row 2 minus row 1, we have 0, 5, 5, minus 25, 0. Replacing row 3 with row 1 minus row 3, we have 0, 8, 6, 22, 0. And then now replacing row 1 with 1/10 of row 1, so we return to this state, we have this. Okay, next, we want our second pivot to be where this 5 is. I can see each of these entries are divisible by 5, so I can divide by 5 or multiply throughout in that row by 1/5. But in anticipation for this 8 here, I can see that 8, 6, and 22 they're all divisible by 2. So I want to multiply row 3 by 1/2. I will get a 4 when I do that. So I really want this to be 4 here and this to be 4 up here. So what we're going to do then is multiply row 1 by 4, multiply row 2 by 4 over 5, 0, 4, 4, minus 20. So 1/5 of 25 is 5. 5 times 4 is 20. So we get minus 20 here. There's a negative there. Okay, now the third row I want to multiply by 1/2. So 0, 4, 3, 11, 0. Okay, so now everything in this second column is a 4. That makes it easier to have zeros above and below our second pivot, which is here. I'm going to circle the pivots now. So now we want 0 above and below this second pivot. And so we want to replace row 1 with row 1 minus row 2. 12 minus 20 is 32. Let's replace row 3 with, using row 2 where our pivot is, row 2 minus row 3. So 0, 0, 1, minus 31, 0. And let's replace row 2 just with itself. Okay, so we have a pivot here, and a pivot here. We want zeros above that pivot. And so now I want to multiply the bottom row by 4 because I have 4s here. Okay, and so we can now get zeros where those two 4s are that I have circled by replacing row 1 with row 1 minus row 3 and replacing row 2 with row 2 minus row 3. Okay, now row 3, let's just multiply that by 1/4. Okay, similarly, we're going to multiply rows 1 and 2 by 1/4. And so now we have the row reduced echelon form of the original matrix. Okay, so what does this tell us? Well, if we go back to this equation right here, we now have an alpha, beta, gamma, and delta, all in terms of delta. So this says that alpha plus 39 delta equals 0, beta plus 26 delta is 0, gamma plus minus 31 delta is 0. And so we can express alpha, beta, gamma, and delta all in terms of delta. So alpha equals minus 39 delta, beta equals minus 26 delta, gamma equals 31 delta, and delta equals 1 delta. Okay, now going back to that equation, assuming delta is non-zero, we can divide throughout by delta. And so this tells us then that minus 39 U1 minus 26 U2 plus 31 U3 plus U4 is the 0 vector. And so then we see that the vectors U1, U2, U3, U4 are linearly dependent because these coefficients here are not all forced to be 0. And in fact, U4 depends on U1, U2, U3 because we can take these over to the other side of the equation and express U4 in terms of U1, U2, and U3. So they're dependent. Okay, question 4, part B. Determine whether U, V, and W are linearly dependent or independent. Okay, so again, we can just put these in columns, but I'll walk through the background of this. So assume alpha U plus beta V plus gamma W is the 0 vector. Okay, and so then what that would say is alpha, 2 alpha, 5 alpha plus 2 beta, 5 beta, beta plus gamma, 5 gamma, 2 gamma is 0, 0, 0. Now adding these together, we have alpha plus 2 beta plus gamma must be equal to 0. We have 2 alpha plus 5 beta plus 5 gamma must be equal to 0. We have 5 alpha plus beta plus 2 gamma must be equal to 0. This is a simultaneous system, right? This gives rise to a matrix equation, and that is the matrix equation 1, 2, 1, 2, 5, 5, 5, 1, 2, alpha, beta, gamma equals 0, 0, 0. Now to solve this, we can write the augmented matrix. So the augmented matrix is, notice what the columns are, U transpose, V transpose, W transpose, 0 vector transpose. So let's note this because some people like to go straight to this point, which is fine, I think. Okay, and this is the matrix 1, 2, 1, 0, 2, 5, 5, 0, 5, 1, 2, 0, which we are going to row reduce, seeking the row reduced echelon form of this matrix. Okay, so the GCD of 2 and 5 is 1. The least common multiple of 2 and 5 is 10. So we want to have 10s in this first column. So I will multiply the first row by 10, the second row by 5, and the third row by 2, like so. I want to replace row 3 with row 3, or row 1 minus row 3. Okay, and so that is 0, 18, 6, 0. I want to replace row 2 with row 2 minus row 1. I'm always using row 1 where my pivot is. So 0, 5, 15, 0. And let's multiply row 1 by 1/2 in anticipation of using this 5 there. So half row 1, so we have 5, 10, 5, 0. Okay, so now having this 5 as my next pivot, let's deal with these two first. So I will multiply row 2 by 2 and multiply row 3 by 1/6. Okay, there we go. Now using this pivot in the second column and second row, let's replace row 1 with row 1 minus row 2. We have 5, 0, minus 25, 0. Okay, now I want to, and in anticipation of using this 3 down there, I want to multiply row 2 by 3/10 of row 2. So we have 0, 3, 9, and 0. Keeping row 3 the same for now. Okay, next, we want to have a 0 here under this second pivot. So let's replace row 3 with row 2 minus row 3. Let's replace row 2 with 1/3 of row 2. Let's replace row 1 with 1/5 of row 1. Okay, now we have an 8 down here. This is our third pivot. We want that to be a 1 eventually. Okay, but we can see that since we can make this a 1 by multiplying that third row throughout by 1/8, we will be able to make zeros here just by using this. So our row reduced echelon form will be exactly this, with the identity matrix here on the left and zeros here. So what that tells us then is that alpha U plus beta V plus gamma W equals 0, alpha equals 0, equals beta equals gamma. So we're forced to have alpha, beta, and gamma all 0. So U, V, and W are linearly independent, like that. Question 4, part C. We have U is the vector 1, 2, 3. V is the 0 vector 0, 0, 0. W is 1, 5, 6. Now notice, we have the 0 vector in there, so this tells us straight away we are going to see that these 3 vectors are linearly dependent. Okay, let's see how. Choose 0 times U plus 0 times W plus any other number, say 1 times V. What is this? Well, we have the 0 vector then, plus the 0 vector, plus the 0 vector. Of course, that is the 0 vector. These coefficients are not all 0. So 0, 1, and 0 are not forced to be all 0. And so then the vectors U, V, and W are linearly dependent. Okay, question 5, part A. Determine whether or not the following four form a basis for 3 space, well, the vectors 1, 1, 1 and 1, 0, 1 do not form a basis for 3 space, and the reason why is because they're not enough. Since the dimension of 3 space is equal to 3 and 2 is less than 3. So a basis for an n-dimensional space requires n vectors to form a basis. We need n vectors, and those vectors must span that space, meaning we must be able to obtain any vector in that vector space as a linear combination of those basis vectors. So this cannot be a basis for 3 space. All right, moving on to part B, we have the vectors 1, 1, 1, 1, 2, 3, and 2, minus 1, 1. Do these form a basis for 3 space? So first we need to decide whether or not these vectors are linearly independent. If they are linearly independent, then since there are enough of them, they should also span 3 space. So let's find out, are these dependent or independent? Okay, so we set up our equation. Now what this will do is it will give us the matrix equation of the transpose of each of these, 1, 1, 1, 1, 2, 3, 2, minus 1, 1, times alpha, beta, gamma equals 0, 0, 0. Okay, and so we can row reduce this, or we can just take the determinant of that matrix on the left, since it's a square matrix. If the determinant is non-zero, then we can multiply by the inverse of that matrix, and we would get alpha 0, beta 0, gamma 0. But if the determinant is equal to 0, then we would see that the 3 vectors are linearly dependent, because alpha, beta, and gamma would depend on each other. So in this case, let's form the augmented matrix and row reduce that. Okay, now replacing row 2 with row 2 minus row 1, 0, 1, minus 3, 0. Replacing row 3 with row 3 minus row 1. Okay, next, we want to 0 where this 1 is, so let's use this second pivot here to get a 0 there, and then eventually we want to 0 down here with the 2 is also. So replacing row 1 with row 1 minus row 2, 1, 0, 5, 0, multiplying row 2 by 2 so that we can get a 2 there and deal with this 2, and we'll keep row 3 the same this time. Okay, next we want to replace row 3 with row 3 minus row 2 so we can get a 0 here, and the entries of row 2 are divisible by 2, so let's multiply by a half. Okay, replacing row 1 with row 1 minus row 3, replacing row 3 with 3/5 of row 3, and finally replacing row 2 with row 2 plus row 3 gives us this so far, and replacing row 3 with 1/3 of row 3. So we have the identity matrix on the left, zeros on the right, and so what this tells us then is that alpha is equal to 0, beta is equal to 0, and gamma is equal to 0. So all of the coefficients are forced to be 0. So what we see then is that the 3 vectors are linearly independent. Okay, so that also tells us that the determinant of this matrix here on the left is non-zero. That matrix is invertible. So it also tells us that these 3 vectors span all of our 3. Okay, so let's say also span of the 3 vectors is equal to R3, because since if the vector PQR is an arbitrary vector in R3, then we can always find coefficients A, B, and C that are real numbers, such that A times 1, 1, 1 plus B times 1, 2, 3 plus C times 2 minus 1, 1 is equal to P, Q, and R, no matter what numbers P, Q, and R are, because there's another rearrangement of this So let's just say because equivalently, we have this matrix equation equal to PQR. And since this matrix here on the left is invertible, okay, I've run out of paper, so I'll grab some more here. And since the matrix is invertible, and we know that because that row reduced echelon form gave us the identity on the left, so we know that the matrix is invertible. So we get, and let's just call this uppercase A, we get lowercase a, b, c equals A inverse times PQR. So this tells us we can always solve for A, B, and C in the set of real numbers, satisfying this irrespective of the values of P, Q, and R. Okay, so that tells us that if you give me any vector in 3 space, I can give you 3 coefficients A, B, and C such that these 3 vectors form with a linear combination your vector PQR. Okay, and so the span of the 3 vectors is equal to 3 space. Okay, now since we have those two things, the span of the 3 vectors is 3 space and the 3 vectors are linearly independent. So we learn that the 3 vectors in a set of 3 vectors is a basis for 3 space. Okay, so you see that a basis for a vector space is not unique. What is unique about the vector space is the dimension, or the number of vectors required to form that basis. That's what's unique about it. So the dimension is an invariant of the vector space. The basis itself is not. Okay. Question 5, part C. So here we have 4 vectors in a 3-dimensional space. Well, that's too many. So to be a basis, we require exactly 3 vectors to span a 3-dimensional space, and those 3 vectors must be linearly independent. Okay, so if we have 4, then the 4 vectors must be linearly dependent. Now, how can we do this? So let's write 1, 1, 1, 2 in our top row. So what I'm doing here is I'm putting 1, 2, 3 in my first column. I'm transposing the first vector, putting it in the column. The second, I am transposing the 1, 3, 5, then 1, 0, 1, then 2, 3, 0. So I've transposed each of the vectors and concatenated those into a matrix. Now, if we row reduce, taking the row reduced echelon form of this, what we're going to get is 1, 0, 0, 9, 0, 1, 0, minus 5, 0, 0, 1, minus 2. Okay, and so you can do that by hand. You can do it in Mathematica. You can do it in MATLAB, and so on. And so what this says is that 9 times the vector 1, 2, 3 minus 5 times the vector 1, 3, 5 minus 2 times the vector 1, 0, 1 is equal to the vector 2, 3, 0, which you can check. And so we see this 4th vector is dependent on these other 3 vectors here. And so hence linearly dependent and not a basis for 3 space. Okay, alternatively, what we can do is seek a simpler spanning set for the 4 vectors. So let's write that down. What we want to do in this case is write these as rows of a matrix. So 1, 2, 3, 1, 3, 5, 1, 0, 1, 2, 3, 0. Row reduce that. Now when we do, we're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. So again, this tells us that these 4 vectors are linearly dependent. Okay, so what is a simpler spanning set? It will just be 1, 0, 0, 0, 1, 0, 0, 0, 1. So let's conclude, because what we're doing here is we're taking linear combinations of these to form the equal span of 1, 0, 0, 0, 1, 0, and 0, 0, 1. There we go. Question 5D. Here we have 3 vectors in 3 space. So we don't know at this point, just by looking at them, whether or not they're linearly independent and span 3 space. Okay, so there are several ways to tackle this problem, at least 3. So let's say let u equal the vector 1, 1, 2. Let's let v be equal to the vector 1, 2, 5. And let's let w be equal to the vector 5, 4. Okay, so seeking a simpler spanning set, we take these vectors and put them into rows of a matrix, U, V, W, like this, is 1, 1, 2, 1, 2, 5, 5, 3, 4. We row reduce this, taking the row reduced echelon form of this matrix. What we're going to get is 1, 0, minus 0, 1, 3, 0, 0, 0. Okay, so what this says then is that span of U, V, and W is equal to the span of these two vectors here, 1, 0, minus 1, and 0, 1, 3. Okay, how many are there? There are 2. So since there are 2, and we need 3 linearly independent vectors to span the entire space, that's not enough. So we see that these 3 vectors are linearly dependent and cannot span all of our 3. So not a basis for our 3. Okay, now alternatively, we can take these, transpose them, right? Alternatively, U transpose concatenated with V transpose with W transpose. We have 1, 1, 2 in the first column, 1, 2, 5 in the second column, 5, 3, 4 in the third column, and then we row reduce this, and we will get 1, 0, 7, 0, 1, minus 2, 0, 0, 0. Okay, now identify where our pivots are. We have a pivot here, and we have a pivot here. There are only 2 pivots. So to find a simpler spanning set, what we do is we identify which columns these are in, look at the columns of the original matrix, and so we can see that that is U transpose V transpose. So we learn then that span UVW is equal to span of U and V. So again, we see that this is not a basis. Okay, and so furthermore, from the point of view of linear independence and dependence, if you were to just include another column containing all zeros in here to seek A, B, and C such that AU plus BV plus CW is the 0 vector, what you would learn then upon row reducing that is you would get this including another column of zeros. But what that would tell you is that the coefficients A is 7, B is minus 2, and C is 0. Or that just says 0 equals 0. Okay, so then what we see is that 7 times U minus 2 times V is equal to W. And so you can check that as well. 7 minus 2 is 5, 7 minus 4 is 3, and 14 minus 10 is 4. So that works out. Okay, alternatively, again, so the determinant, and this is probably the easiest way to do this problem, not the most insightful, determinant of U transpose V transpose W transpose is 0, so U, V, and W are linearly dependent. And so again, we don't have a basis for 3 space from U, V, and W. Okay, question 6. Determine whether the vectors, there are 4 vectors there, form a basis for 4 space. If not, find the dimension of the subspace that they span. Okay, so I'm going to label these. Let's let P equal the first vector, Q be the second vector, R be the third one, and let's let S be the fourth vector, 2, 6, 8, 5. So here we want to seek a simpler spanning set of this because the last sentence says, if not, find the dimension of the subspace that they span, so we can just count the non-zero rows of the row reduced echelon form of P, Q, R, S put into rows. So let's form that matrix. So I've put P in the first row. I'm going to put Q in the second row. 1, 2, 3, 2. R in the third row. 2, 5, 6, 4. And S in the fourth row. And now we want to row reduce this. So I'll do this by hand for your sake. Okay, so I like that 1 there in the top left entry. So let's replace row 2 with row 2 minus row 1. So we have 0, 1, 2, and 1. Now, in anticipation of dealing with the 2 2's down here, I'm going to multiply the top row by 2 for now, just to make the arithmetic a little easier later. Okay, so this was row 2 minus row 1, and this is 2 row 1. Okay, next, we want zeros where these 2 2's are, and so we are going to use our pivot there in the top left entry to do that. So next we have let's replace row 3 with row 3 minus row 1, and we'll replace row 4 with row 4 minus row 1. So row 3 minus row 1 gives 0, 3, 4, 2. Row 4 minus row 1 gives 0, 4, 6, 3. And let's keep row 2 the same for now. Let's multiply row 1 by 1/2, so we return it to the ones. Okay, so now we have our pivot there with zeros below it, so that's good. Now let's have this one here be our second pivot. So we want 0 above and we want zeros below. So let's now replace row 1 with row 1 minus row 2. So we have 1, 0, minus 1, 0. Next, we're going to get a 0 where that 3 is. So I want to multiply row 2 by 3. So 0, 3, 6, 3, 0, 3, 4, 2. That's row 3. And then we'll leave row 4 as is for now. Okay, so now we want to replace row 3 with row 2 minus row 3. So we have 0, 0, 2, 1. Okay, and now let's, in anticipation of getting a 0 where that 4 is, let's make this 3 a 4 by multiplying row 2 by 4/3. So we have 0, 4, 8, and 4. Let's keep row 1 as is and row 4 as is for now. Okay, so next we want to replace row 4 with row 2 minus row 4. So we have 0, 0, 2, and 1. And here we have 0, 0, 2, and 1. That's row 3. Now let's replace row 2 with 1/4 of row 2. So we have a 1 there again. So 0, 1, 2, 1. Let's replace row 1 with row 1. So 1, 0, minus 1, 0. Okay, next we can see that rows 3 and row 4 are identical, so we can replace row 4 with row 3 minus row 4, and that's how we get all zeros down the bottom. Okay, and so also we can see that we can get zeros right here by replacing row 2 with row 2 minus row 3. So we'll get 0, 1, 0, 0. And then let's now keep row 3 as is for a moment. And in anticipation of having a 0 where that minus 1 is, let's multiply row 1 by 2. So we'll have 2, 0, minus 2, and 0. Okay, next I am going to replace row 1 with row 1 plus row 3. So we'll have 2, 0, 0, 1. Let's keep row 2 the same for now, and let's keep row 3 the same for now, and keep row 4 the same. Okay, so now we have a diagonal there. We don't have ones on that diagonal, so we need our pivots to be ones, but I like to do this in the last step. So what we'll do now is multiply row 1 by 1/2, row 3 by 1/2, and so we'll get 1, 0, 0, 1/2, 0, 1, 0, 0, 0, 0, 1, 1/2, and 0, 0, 0, 0. Okay, so now this is in row reduced echelon form. Now what does it say? We can see that those 4 vectors P, Q, R, S are linearly dependent because we have a row of zeros. In other words, what this is telling us is that the span of P, Q, R, and S is equal to the span of the vectors 1, 0, 0, 1/2, 0, 1, 0, 0, and 0, 0, 1, 1/2. Okay, so how many are there here? There are only 3. So the dimension of the span of P, Q, R, and S is 3. Now, does that answer the question? Find the dimension of the subspace they span of R4. So this is the subspace that these 4 vectors span. It's spanned by 3 vectors. So that is a proper subspace of 4 space. The dimension is 3. Question 7. Extend U1 equal to 1, 1, 1, 1 and U2 equal to 2, 2, 3, 4 to a basis. for R4. Okay, so what I suggest that we do is seek a simpler spanning set for U1, U2. So I'll say we first seek simpler looking spanning set for U1 and U2. Okay, and so let's take these two vectors, put these in rows of a matrix, as rows of a matrix. And so we have 1, 1, 1, 1, 2, 2, 3, 4. And I want to take the row reduced echelon form of this. So we have, let's multiply row 2 by, let's multiply row 1 by 2. And then let's replace row 2 with row 2 minus row 1. So we have 0, 0, 1, 2. Let's replace row 1 with 1/2 of row 1. So 1, 1, 1, 1. Okay, so next let's replace row 1 with row 1 minus row 2. We have 1, 1, 0, minus 1. And let's keep row 2 the same. Okay, so we have a pivot here, we have a pivot here. This is in row reduced echelon form. So to extend this to a basis for R4, I want to have a pivot. I want to extend this matrix so that I have a pivot in the second column and I have a pivot in the fourth column also. So extending U1, U2, and then I'll put 0, 1, 0, 0, and I'll put 0, 0, 0, 1. Now this should be a basis for R4, since when I put these into rows of a matrix and row reduce this, what we get then is 1, 1, 0, minus 1, 0, 0, 1, 2, 0, 1, 0, 0, 0, 0, 0, 1. Okay, and now we can do row swaps so that this one goes here and this goes here. And now looking at this, it's clear that this will row reduce to the row reduced echelon form. That is the identity matrix, 4x4 identity matrix. And we know that E1, E2, E3, E4 forms a basis for R4. In other words, the rows of this final matrix here form a basis for R4. And so we have successfully extended U1, U2 to be a basis for R4 by including this vector and this vector. Question 8, part A, determine whether the following vectors in 4 space are linearly dependent or independent. So here let's let U be equal to 1, 2, minus 3, 1. Let's let V be equal to 3, 7, 1, minus 2. And W be equal to 1, 3, 7, minus 4. So what I want to do here is take U transpose concatenated with V transpose and W transpose and form a matrix. So that's the matrix. In column 1, we have 1, 2, minus 3, 1. Column 2 has 3, 7, 1, minus 2, and column 3 has 1, 3, 7, minus 4. Okay, and so let's row reduce this matrix. So let's replace row 4 with row 1 minus row 4. So we have 0, 5, 5. Let's multiply row 1 by 2 in anticipation of zeroing this 2 here in the first column. So we have 2, 6, 2, then we have 2, 7, 3, and then we'll keep row 3 the same for now. Okay, so next, let's replace row 2 with row 2 minus row 1. So we have 0, 1, 1. Let's replace row 1 with 3 over 2 row 1. So we have 3, 9, 3. Then row 3 will keep the same here. What I want to do is, in the next step after that, deal with these two so we get a 0 here. And let's replace row 4 with 1/5 of row 4. So 0, 1, 1. Okay, so next, let's replace row 3 with row 1 plus row 3. So we have 0, 9 plus 1 is 10. 3 plus 7 is 10. Now you can see that row 2 and row 4 are the same. So let's replace row 4 with row 2 minus row 4. So we have 0, 0, 0 for that then. 0, 1, 1 for row 2. And let's replace row 1 with 1/3 of row 1. So returning it to the original row 1. 1, 3, 1. Okay, now we can see that row 2 and row 3 are multiples of one another. So let's replace row 3 with row 2 minus 1/10 of row 3. So we have 0, 0, 0, row 4, 0, 0, 0, and let's keep row 2 the same for now, and we'll replace row 1 with row 1 minus 3, row 2. So that would give 1, 0, minus 2. Okay, so now that's in row reduced echelon form, but what does this tell us? So this tells us that if we were looking at AU plus BV plus CW is the 0 vector, then we would do some mathematics, obtain this matrix. In other words, what we would have then is U transpose concatenate V transpose concatenated with W transpose times ABC is 0, 0, 0. And so then from this, we would get the augmented matrix, which would row reduce to 1, 0, minus 2, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then from there, we could read off A, B, and C. So this tells us that A equals minus 2, B equals 1. And so what we work out then is that minus 2U plus V minus W equals the 0 vector. And so W is minus 2U plus V. And we see that UV and W are linearly dependent because W depends on U and V. Linearly dependent. Question 8, part B. So this time, let's let P be equal to 1, 3, 1 minus 2, Q be equal to 2, 5 minus 1, 3, and R be equal to 1, 3, 7 minus 2. Okay, are these three vectors linearly dependent or independent in 4 space? So if we take P transpose concatenated with Q transpose, concatenated with R transpose, then we have 1, 3, 1 minus 2 in column 1, 2, 5 minus 1, 3 in column 2, 1, 3, 7 minus 2 in column 3, and row reduce this. What we're going to get is 1, 0, 0, 0 in column 1, 0, 1, 0, 0 in column 2, 0, 0, 1 in column 0, 0, 1, 0 in column 3. So this tells us that the three vectors PQR are linearly independent. And so specifically, it tells us that the span of PQ and R is equal to the span of PQ and R, and it doesn't reduce anymore. Okay, so alternatively, if you were to take these and place them as rows of a matrix, 1, 3, 1 minus 2, 2, 5 minus 1, 3, 1, 3, 7 minus 2, and row reduce this, we would get 1, 0, 0, 19, 0, 1, 0 minus 7, 0, 0, 1, 0. And so that says then that span of PQR is equal to span of these simpler looking vectors, 1, 0, 0, 19, 0, 1, 0 minus 7, 0, 0, 1, 0. Okay, and so we can see that there are 3 of them. We require 3 of them. So we learn that these are, again, linearly independent. We need 3. Okay, question 9, part A. Now, you've already seen a lot of hand calculations, so I'm going to do this one in Mathematica. All right, so determine whether the following polynomials U, V, W are linearly dependent or independent. So what I want to do is place the coefficients of U into a matrix. So let's begin. So I've got them written here. I'm going to insert in Mathematica a matrix with 4 columns and 3 rows, and then place the coefficients. They've got to be in the correct order. So 1, minus 4, 3, 3. Then we have 1, 2, 4, minus 1. Then we have 2, minus 1, minus 3, 5. Okay, and so now I am going to write row reduce, slide this over so you can see that, and then display the result in matrix form. So I have handwritten this, what it says there, so we can see that the span of U, V, and W is the span of the vectors in the rows here. And so in this case, U, V, and W are linearly independent because we still have 3 of these. We do not have a row of 0. So linearly independent. Okay, now for part B, I'll copy this and then I'll just change the numbers. So in the first row, we'll have 1, then minus 5, minus 2, 3. Then we have 1, minus 4, minus 3, 4. Then we have 2, minus 17, minus 7, and 9. So let's do the same thing. Row reduce this, displaying the result as a matrix. I'll copy that result down here. So here we see then that a reduced spanning set is spanned by the vectors 1, 0, 0, 1, 0, 1, 0, 0, and 0, 0, 1, minus 1, corresponding to polynomials t cubed plus 1, t squared, and t minus 1. So again, u, v, and w are linearly independent.